Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Got radio, Chris?
Well, I guess this is the best I can do today, Jesse. So.
Do we have not 100% Chris right now? What does that mean?
No, it doesn't mean that at all.
Okay.
It's just sometimes I wish I had a better radio voice. I've got this radio face to go with it, but I don't have. I need this more of a baritone kind of thing going on.
I don't know, man. I think you got a good radio voice. You have a commanding presence. You've got some authority that conveys through that voice. I like it. I could listen to Chris Bolhuis at 2:30 a.m. while driving across the country, and he wouldn't put me to sleep necessarily, I don't think.
I'll tell you what, I put my mom to sleep. Every time I go over there on Friday afternoon, she's listening to our podcast, and she's sleeping. I'm starting to think she stages it this way now.
Yeah, she might do. Any new words from Joyce? Any update from Joyce recently?
Oh, no, but they just listened to the episode where we were ripping on my dad's the way he talks and his strong diaphragm.
What were the repercussions about that one?
So I asked my mom, because my dad hadn't joined us yet, and I said, is he mad at all? And she said, oh, no, we laughed our butts off about that, and, they were fine.
Okay, good. All right. I mean, that's the good thing about the Bolhuis family, the Bolhuis clan, is you're pretty good-spirited with giving each other a hard time.
Yeah, we try not to take each other too seriously.
That's right.
Or take ourselves too seriously.
That's right. So it's good fun over there at Bolhuis clan.
That's right. Hey, one thing too, totally off topic, but we're interviewing for new teachers, and you said something about a presence, and it is really interesting when you have people that you've never met before, they're interviewing for a job. It's just so interesting when people walk into a room and some people have that immediate presence about them and some people just don't. I haven't been a part of interviews for quite a while. It's been a long time. Okay. And I was just reminded of that. Like as soon as somebody walks in a room, some of them, they just have that presence and then others don't. I don't know it's an interesting thing to think about. And what makes that.
I think for me, this is my opinion, because there's a lot of conversation in, let's say, higher ed about the value of advanced degrees. Like, what is the value of a master's and a PhD? And this is one thing that I think is really valuable because Chris, when you're presenting as a teacher, you're presenting all the time. So you kind of have to be good at it. You have to either develop that skill set, that presence, or you've developed it earlier in life or something. But is one thing that in graduate school, I think you kind of have to build and you become good at is that presence. You walk up there, you're presenting your work, your thesis, or you're giving a talk somewhere. You have to have it, and you work really hard at those soft skills, at developing those. So I think it is something that you can learn. I certainly didn't have it early on, and I've developed.
Do you have it now?
I think so. I think in a classroom, I've developed a bit of a presence, or at least, and I think it's that confidence. I don't know. For me, it was that confidence, like building up confidence so that I knew that I could answer any question that was thrown at me, or at least deflect confidently, right? It was a little bit of internal confidence that had to be built up to get to that level. I don't know. What do you think?
I think it is confidence. It's really hard to put your thumb on what that is. Some people just automatically command a room, and I don't really know what that is. And it's hard to develop something that I can't even really quantify. I don't even really know what a presence is other than it's a good way to describe it, but I still don't know what it is.
And it's so interesting to watch. I've seen this, several times including in my own development, is watching a student go through graduate school and you see them develop their presence. We actually had one of the graduate students in our group just defended her PhD and did an amazing job at it. And she was always pretty good, had a pretty good presence, but now she's like, it's a no joke presence. Like, she walks into the room and you're like, oh, okay, this is somebody where everybody perks up their ears, right? So it's really fun to watch that development over the course of a degree program, right? I'm sure it's the same for you. Like, you're on the maybe older end of the teacher spectrum. You probably have seen young teachers kind of develop it over their time, maybe, or
absolutely. Yeah, for sure. You get to watch that happen. It's kind of a cool thing to see. I have a question for you, Jesse. Then when they defend and they do this successfully, it's got to be a really intimidating environment, by the way. Do you make them, when they walk out of the room, do you bring them back in and call them doctor?
Yeah. Oh, of course. Yeah, for sure. I mean, at a PhD, the defense is usually a little bit more lighthearted than the earlier tests you take. Like you take a test in your second year and third year, and those are more, there's more risk. By the time you finish a PhD, you've written a thesis. It's just how well do you do? Like you're going to probably pass by that point. But yeah, I mean, it's a great thing. You come in, the supervisor usually goes and gets them from the hallway. You kick them out into the hallway while the committee discusses, okay, how do we do? What recommendations do we have, et cetera. And then the person goes and gets them and says, oh, well, congratulations, Dr. So-and-so. And everybody goes and shakes their hands, gives hugs all around. It's really nice. And then usually have a little party get together at that evening or at some point to kind of celebrate it. And everybody is calling him doctor. It's great. I remember it. Actually, I probably have it here on the shelf.
All I see are the Harvard classics behind you.
Yeah. Where did it go? Okay. This is funny. My wife has removed it from my shelf. It used to be there. Well, I'll have to get on her. Where'd she put it? One of my friends who's a faculty member in Alberta got me a knife and they had engraved Dr. Reimink on it. And gave it to me that night. It's just so fun. Yeah, totally cool.
Well, she took it because she's the real doctor in the Reimink household.
Yeah, exactly right. She probably took it. Yeah, it's probably on her desk.
That's right. She earned it.
Anyway, it is a cool moment. So, yeah, that's interesting. Well, I don't know how we transition, Chris. How do we transition into what we're talking about today?
We just jump. We just go.
Okay, let me try one. Here we go. These rocks that we're talking about, or really the minerals, they have a presence because they've been around a long time and they've developed a presence.
That's good, Jesse. Nicely done. By default, these zircons have a presence.
You can feel when they're around, right? We're talking about today, and this is, if you're in the podcast, this is part 1 of 2. We're going to have 2 episodes on this, but these are the oldest fragments of Earth. And that's a really important qualifier. These are not the oldest rocks on Earth, but they are the oldest fragments of Earth that we know of. Chris, what do you think about this topic? What's your knee jerk?
Well, first of all, I had never heard. We are going to talk in these 2 episodes. We're going to talk about what's called the Jack Hills zircons. Jesse, I've never heard of this before. Maybe, I don't know, 3 or 4 weeks ago, I've never heard of the Jack Hills zircons. When did you come across this in your educational career? Because you right away, when you went to graduate school, you started digging into Earth's oldest material. So I would assume you came across this pretty soon.
That's right, Chris. I think right away during graduate school, at the start of graduate school. And it's, once you've heard of these, you'll start to see, I'll be interested to see, Chris, over the next month or 2, I bet you're going to see more news articles that kind of mention them, these geology news publications. A lot of publications on the Jack Hills get a lot of press because it's hey, we discovered, quote unquote, discovered, as we'll talk about, discovered some signal about plate tectonics starting 4.4 billion years ago. And all that evidence is based on the Jack Hills. So you'll kind of see more of this. I guess my point is, I bet some of our listeners for sure have heard of these because they pay attention to the geology news sphere and have heard of these zircon grains.
All right. So Jesse, give us the 30-second overview then of what is it? What are the Jack Hill zircons? And again, just kind of tie this into the discussion about when plate tectonics began on planet Earth.
Yeah. So what these are the oldest fragments of Earth, and they're found, these are individual zircon grains. So they're grains of a rock. A rock is made of minerals. They were crystallized from a magma. That magma formed a rock. That rock was eroded. And these zircons are the only things that have survived, the only things that we know have survived from that rock. And so we find these little zircon grains. Now, if you're in the app, you can go to image number 2 in your stack here. This is a photo of the Jack Hills, the rock that contains the Jack Hills zircons. It's a conglomerate. So these things now are found in a conglomerate that has sand grains in it and cobbles. And some of those sand grains are really, really old zircons, older than 4.2 billion year old zircons.
Older than 4 point what?
4.2. Yeah. So some of them go up to 4.35 or 4.38 billion years old.
Okay, so let me just back up a minute. I want to just make sure that we set the stage in the right ways to bring everybody along. First of all, this is a gorgeous rock. I love conglomerate anyway.
I do too.
This is a really pretty rock. So I just want to make sure that our listeners understand that this came from a felsic magma. these zircon grains initially were probably a part of granite, right? Because zircons grow in that kind of magma as opposed to more of an intermediate or mafic basaltic kind of
One quick modification to that, Chris, is that zircons do grow in intermediate rock. So probably not basaltic, but kind of any other rock type. I mean, not mafic or ultramafic, but any kind of intermediate to felsic rock mostly has zircons in it. So yeah, I would broaden that, and that'll come back in probably the second episode we have on this. We'll talk about the debate here because there's a ton of scientific debate about these. So it could be intermediate or it could be granitic.
So what we're saying then is those rocks formed, and especially if it was granitic, these formed quite deep inside the earth. Then they have to get brought to the surface through weathering, erosion, isostasy, this kind of uplift that happens with that. And then it has to get weathered out of the rock and carried to where it is now in Western Australia and deposited. Do we know when this conglomerate was deposited?
Yeah, well, yes, mostly. It's between 3 billion and 2.7 billion years ago. So it's a very old sediment. I mean, it's a 3 to 2.5 billion year old sediment. And part of its material, part of the cargo that's in that sediment is really old. And so, Chris, this is something that I think is often confusing here, and you laid it out really nicely. That sequence of events, you have to have a magma that crystallizes, so the zircon grows there. That zircon is included in its parental rock. That parental rock is exposed at the surface. It's weathered, eroded. The zircon is the one that survives. All the quartz and feldspar and all the other stuff gets eroded out, and the zircon's the only one that survives. So that was
only
very, very nicely put.
That's right. Yep.
Yeah, that's exactly right.
Well, if you think about that, so the zircon grains are 4.38, almost 4.4 billion years old. And this Jack Hills conglomerate was deposited 1.3 billion years later.
Yeah.
I mean, that's a tremendous amount of time right there. I mean, that's just insane to me.
So Chris, let me interject one part about this rock. The rock's around 3 billion years old. It's a really, really restricted area where the old zircons are found. So like one outcrop, basically, that most of the zircons come from. There's a bunch of old zircons in there. Some go really old, up to, you said, 4.38, which is the oldest one. But, there's a bunch of 4.1 billion year old zircons. There's a bunch of 3.9 billion years. So there's a huge range of ages.
They're just babies.
They're just
babies.
Just little babies.
So now, okay, hold on, Jesse. So first of all, why is it such a restricted area? Why are they in this one spot, the truly old ones? How come?
Now, it's a really hard question to answer confidently, but let's use an analogy. If you think of a stream in the Rockies, the Rocky Mountains, or in the Alps, or whatever mountain range you want to think about, that stream is going to be a conglomerate someday. It's got a bunch of boulders in it, a bunch of cobbles, and sand.
Fast-moving, high energy.
Fast-moving, exactly. Think about how, let's say, gold exploration companies explore for gold. They take stream sediment samples. And so if you're at the mouth, right out by Denver, where the big river flows out onto the plains, you're going to collect some stream sediment samples. If you find gold there, you're going to say, oh, somewhere upstream, there's gold. And you're going to work your way upstream and sample and sample and sample. You're going to sample the tributaries. You're going to sample all over the place till you find where you don't have gold anymore. Then you can rule out some part of that tributary. And you're going to focus in on like where you have gold. You could do the same thing with old zircons, because the old rocks might have only been exposed in one small tributary part of the stream. And so they're only deposited in one little tributary branch, not in the big stream, or at least they're much more infrequent. The Mississippi has very few really old zircon grains, but if you get to some tributary up in Minnesota, there's a lot of old zircon grains there. So it's just really localized, like where these rocks...
So these zircons are a lot like a placer deposit then, kind of panning for gold.
That's exactly
they're strong,
right, Chris.
They're dense, they're chemically very, very, very stable.
Hold on. I want to say that is a really, really good analogy. They are just like a placer deposit. Think about trying to find gold nuggets somewhere. It's going to be a very restricted area that they're found. And the same thing goes for these zircons.
All right. So then let me ask a follow-up question to this then. Well, maybe a couple. Is this place really difficult to get to, and have you ever been there?
So no, I've never been, and yes, it's very difficult. It's very remote part of Western Australia in what's called the Yilgarn Craton. It's an old block of crust. We've talked about those before. But yeah, it's very remote. It's very hard to get to, but it's been studied a lot. And so I've never been there. One of my PhD supervisors was there and went there and actually gave me a rock sample from it. So I do have a little treasured rock sample from it, but it's...
you should have that on your desk right now. This
I
should
know,
be,
it's in the office.
You know,
it's because I use it for teaching a lot. You know, my intro level class, probably the first lecture I give, I come and I have the oldest rock and the oldest minerals. And so, you know, students come up and hold them and just trying to get them excited.
Yeah, that's cool. Absolutely. Hey, so where did it come from? Where is the parent rock, this igneous pluton?
As far as we know, destroyed. So we don't really know. And these rocks, these 3 billion-year-old sediments and 2.7 billion-year-old sediments, they're deformed, they're altered, they're old. So we can't really work out where it came from.
When you look at image number 2, then that looks like a metaconglomerate, right?
It absolutely
is.
That's
what we're looking at here.
It's metamorphosed.
This was once just your typical conglomeratic rock that then got subjected to massive amounts of heat and pressure and changed it into something that's a lot more durable than it was when it first formed, probably. Yeah.
If you take that conglomerate, you crush it up, you separate out all the sand grains, all the sand pieces, you're going to get at most a couple percent, up to maybe 4% that are older than 4 billion years old of the zircons. Of the zircons that are older than 4 billion years old.
What are then 96% of them are 3.7 or even younger than
all
that?
The way down to the depositional age, 3 billion years old. So there'll be 3.1 billion year old grains in there too, and those will make up.
Hold on a second.
Fraction.
That's really interesting to me. How would that be possible? How would you get zircons that form in a magma, but they're the same age or maybe a little bit older than the time in which they were deposited? How does that work?
So if you think about the Cascades, right? You know, you've got Mount Shasta, Mount St. Helens blows up, and everything about Mount St. Helens is old.
Can I interject, Jesse? So are you saying then that these zircons, the younger ones, would have formed from more of an intermediate kind of magma rather than plutonic, really, really deep? So they were already exposed at the surface?
It's really hard to tell the difference there, because we're talking about, again, this goes back to what we talked about at the intro chapter of the time scales involved here. We're talking about a 1 billion year age difference. A lot can happen in 1 billion years, right? You can have magmas can be intruded and then exposed on the surface in a couple million years. That's not uncommon to see that happen. So you don't need a long time to get deep-rooted rocks up to the surface. My point about the Cascades, or the Andes maybe, there's sediment being eroded off of those mountains into the ocean basin and being dumped down there. If you go sample those sediments, they're going to have the volcanic arc zircons in them that are 10,000 years old, 50,000 years old, 1 million years old. So you can get sediments that have zircons in them that are basically the same age as the deposition of the sediment. So these are what these kind of zircons look like. And maybe, Chris, we can talk about for the next couple minutes here.
Okay, so can I ask you, that looks like it's really shocked. Is that the case? Are we looking at fractured zircon here?
It's fractured, but that's probably not shocked. Shocked, you'll see very parallel lines all the way through it. But zircon, you bring up a really important point, Chris. Zircon is a really robust mineral. We've talked about this before. It's really reliable. It survives a whole bunch of processes, but it also has this radiation damage. If you go back to our geochronology section, we've talked about that a bunch of different stuff, including the Grand Canyon audiobook. When uranium and thorium decay, they blow apart the grain structure, and that causes this expansion. And so the cracking is usually expansion cracking, because over time, the volume inside is getting bigger because of this decay. And so the outside gets cracked a bit.
And the way that this does that, Jesse, this is by alpha decay, right? And so this is that kind of shot out of a cannon analogy. And is that what is destroying this kind of internal structure?
Yeah. So you take the cannon recoils and it breaks the lattice right around it. There's more volume because it's a broken lattice. It's not nicely bound together. And so if you do that a whole bunch of times over time, and then you can get fluids that percolate in there and can expand it even further. So yeah, those are typically thought of as expansion cracks.
Jesse, what is the basic formula of a zircon crystal?
It's zirconium, Zr, silica, Si, and oxygen. So it's ZrSiO4 is the basic formula. So it's a silicate mineral. It's zirconium silicate mineral.
Okay, and then what is uranium? How does uranium incorporate into the structure then?
It'll go in because uranium can be
to the zirconium.
Yeah, zirconium or silicon site depending, so it'll substitute in there typically, and same for thorium as well.
Okay, yeah. Yep. Okay.
So
Interesting. So you're saying that you do have initial thorium that is a part of the internal crystal structure as well?
that's right. And it's not commonly, it's not as much and it's not as commonly used in zircon, but it is there for sure, like in measurable amounts. And you have a whole bunch of other, rare earth elements. You have all sorts of interesting stuff in the zircon, which we'll come back to in the later episode, next episode.
I just want to say for the listeners, the reason why I asked that question is because that's what uranium decays into. Is thorium is the daughter isotope for uranium-235? Or are we talking about both?
There's two different chains. So there's uranium decays to both decay to thorium, and then the thorium also decays separately. So there's thorium-232 that decays to 208 lead.
Right. So it's an important question because Jesse, as the geochronologist, has to account for how much initial daughter isotope, how much initial thorium was in the crystal structure in order to get an accurate age date on these zircon crystals.
That's exactly right. So, Chris, maybe let's round out this particular episode by talking. So, the Jackal zircons, let's back up. The Jackal zircons, we've talked about where they're found. We've talked about what rock they're in. Maybe we end this by saying what we as a scientific community generally agree upon. And then there's the whole basically next episode is going to be like what we don't agree upon because there's all sorts of different ideas about these zircon grains. But Chris, let me ask maybe what you think about this. Like, why would you think there's so much debate or so little consensus about these grains?
Okay, I don't know. So let me just say what my thoughts are, and let me just start with this. That, it's interesting that you say that these things were deposited 3 billion years ago, 3.0 to 2.7 billion years ago, right? And that means that we obviously had running water well before then. That's a really interesting thing to think about, that planet Earth had running water billions of years ago. I don't know. I find that to be an amazing thing. So I guess why is this important? That's what I'm thinking about. Why is the Jack Hills important? And well, if we had zircon, then we have the kind of magma that is important in making continents. And so it's super important for that because in order to have continents in the way that we think about them today, you have to have plate tectonics. You have to have a mechanism to differentiate this magma, to kind of distill it out enough to get this kind of magma, right? I guess that's why it's important. I don't really know why it's so controversial, though. I don't know.
Yeah. So you're exactly right on both points about the water and the potential for plate tectonics. The difficulty, or the reason, in my view, there's a bunch of different reasons why it's contentious, but one of the reasons is because we're dealing with only zircon grains. Like, we don't have a rock to look at. We don't have all the other minerals. We're looking at zircons, and zircons, we usually look at the zircons and try and see if they are recording the magma they came from properly or accurately. Like, is individual mineral really recording the signatures that are tied up in a rock really well or not? Are there some signatures that they don't record very well? So kind of think of zircon as this beautiful little capsule for age and maybe chemistry. We don't have a rock is the point. We're dealing with individual mineral grains, really. And really, you look at image number 3, and those are 4 different zircon grains that have 4 different histories. They're from 4 different rocks. We can't really interpret them together. You can't say, oh, I saw this signal over here and this signal over here, and therefore 1 + 1 = 2 here. You have to go 1 is 1 is 1 is 1. Like, you can't really combine the signals too well. So
I get that. But the other thing is that zircons don't or very rarely form in mafic magma. And so you say we don't have a rock, but we do know that.
Exactly. So that's the first order thing that we can basically everybody agrees upon. These probably, most people would say these did not form in mafic rocks. These are from, as you said, intermediate to felsic rocks. So we kind of have a whole category of rocks that look like the modern continental crust or look like some things on the moon or Mars. These are probably representing felsic or intermediate rocks. That's one thing everybody mostly agrees upon. So that's one. The second thing that we can broadly agree upon is what you said before, Chris, that these things have indications of water. And you said, okay, yeah, the sediment, the conglomerate, was laid down in water 3 billion years ago. We know that for sure. These zircons, the oxygen in them has a signature of water in them. not water in the zircon, but the oxygen isotopes basically tell us that there was water, liquid water, on the surface of the Earth 4.3 billion years ago. And I think most people, that's widely agreed upon. So we probably had liquid water on the surface of the Earth 4.3 billion years ago. And I don't know if it's important to get into the details of oxygen isotopes, but what do you think?
I mean, we have an image, so we might as well at least talk about it. So, Jesse, when you talk about oxygen isotopes, there are three isotopes of oxygen. There's O16, which is the vast majority of all the oxygen that exists naturally on Earth. And then you have O17 and O18. And we're talking about the atomic mass of the oxygen isotope. So 3 different isotopes. They each have 8 protons in them. They just have slightly different masses, and they get a little bit heavier. So I talk about this when I talk about climate and climate change and some of the evidence for climate change, because it's really kind of a cool thing when you talk about these layers that get deposited, because you get water trapped in seafloor sediment, right? The way that our atmosphere circulates is it's basically driven by what happens at the equator. It's really warm there, and there's just an abundance of water. So you have a lot of evaporation. That water that evaporates out of the ocean makes its way to the poles. It makes its way up to Greenland. It makes its way up to Antarctica. Well, Greenland and Antarctica, they're like 2 to 3 mile thick time machines, because they trap, this ice. They're trapping water, and the oldest stuff is on the bottom of the glaciers, and the youngest stuff fell as snow yesterday. But what they do, though, is they provide this record of how climate has fluctuated over time based upon the dominance of, well, do we have heavy water in the ice or do we have light water? Because during ice ages, heavy water preferentially condenses, and not very much of it makes its way up to the ice caps. And so during ice ages, the ice is loaded with light water isotopes, which means the ocean sediment is richer in heavy water isotopes.
Chris, that's basically the same way we use oxygen isotopes in zircon. And so remember that zircon, ZrSiO4, it's got a bunch of oxygen in it. It's 50% oxygen. Those oxygen atoms and isotopes came from a magma. And so we're using zircon to trace the magma, the original magma composition. Now, the way this works, it's exactly the same way as you described. We have 2 different reservoirs of oxygen on Earth. The ocean is our standard, so we call that 0 by definition. The ocean is 0. When we look at the ratio of 18 to 16 in the ocean, it's 0. The mantle, the rocks in the mantle, are about +5, a little bit above +5. They're +5.5, 5.3. And so if you look at image number 4, if you're in the book, you can see a plot here that shows oxygen isotopes on the left in isotope composition versus age. And this is from my PhD work, but it's a plot that's just showing oxygen isotopes. The gray band there, the vertical gray band, that's the mantle field, and the ocean would be at 0, down below off the chart here. So we have those 2 reservoirs when we talk about rocks and zircons. Ocean is 0, mantle, all rocks start in the mantle, and it's 5.3.
And what you're talking about, though, when you say that, is that it has a much higher ratio of oxygen 18, the heavy
right. There's more 18. There's more 18 in the mantle proportionally than there is in the ocean. So what happens, Chris? So your point's a really good one. If you just take those 2 things and you mix them together, you take 5.5 and you mix it with 0, you're going to get something in between. That only happens at high temperature. So if you have really high temperature, like boiling water, and it interacts with rock, it's going to mix, just straight mixing. But you beautifully said, that bonds with 18 in it are more stable. So if water interacts with rock at low temperatures, like below 100 degrees centigrade, low temperatures, the 18 is going to go into the rock, the altered rock now. So altered oceanic crust, the top layer has higher than 5.5 because it has more 18 in it. Sediments have like 20, plus 20 on this plot. So anything above the mantle field means you had low temperature water on Earth, and that interacted with rock and then melted to form the rock we see today, or the zircon we see today.
The takeaway is we're able to determine something about where the conditions in which that zircon grain formed.
Exactly.
Where did it come from?
And to bring it full circle, you said you can use this, it's a temperature proxy. You use it for ancient paleo temperature. This, we're using it for ancient water-rock interaction temperature. Was it high temperature or low temperature? Same kind of thing. But either way, it's outside the mantle field. The only way to do that is to have water on the surface of the Earth. So that's one thing almost everybody agrees upon. We need low temperature, meaning liquid, water on the surface of the Earth, and that signal is imparted into these zircon grains. So that's something we kind of agree upon. The last thing we agree upon, and this will go back to an episode we recorded on neodymium. I think it was the making magnets or something like that. We talked about using this as a tracer. And there's other elements in the zircon. One of them's hafnium. And basically, it's a radiogenic isotope. We use it as a tracer in the same way neodymium is. We don't need to get into the details, but these tracers tell us that there were older rocks that were melted to form the Jack Hill zircon crystallizing rocks. So there's something older out there that could be older basalt, it could be older felsic crust, but it wasn't just coming out of the mantle. These weren't mantle-derived zircons. They came from some pre-existing crust, either mafic or felsic, that's even older than 4.2 billion years old, or 4.3. So that's the other thing that most people kind of agree upon.
All right. Well, Jesse, then I think that that's a good place to stop. What's coming next is going to be what we don't agree on. But I think most importantly is I want to talk about why. Are we just arguing semantics? Are these small things that are, I want to talk about why there's so much disagreement on this, and because that's what's interesting to me. So, okay.
I agree. And we'll talk maybe just a little bit. We'll tell the brief story of the discovery of these things, which is kind of an interesting thing. Then, yeah, you're totally right. We'll get into the debate. And are these scientists just too in the weeds? That's kind of the question. That'll come in the next part here. So I think, what do you think, Chris? Is that a wrap here for the part one of the Jack Hills? We're not too in the weeds
Absolutely.
yet?
Not yet. Not yet.
We'll get there next time. Hey, that's a wrap. If you are listening on the podcast, thank you. We appreciate it. You can download the CampGeo app, and you can get all the content, including the Jack Hill zircons here in our Earth's Oldest Rocks book. The first link in your show notes is the app. You can go to our website, planetgeocast.com, and click on the link to support us there. We always appreciate that. Send us an email, planetgeocast@gmail.com, and follow us on all the social medias. We're at Planet Geocast.
Cheers.
Peace.